All right, so this week we've been learning limits, which isn't actually part of our textbook. It's more like a supplemental thing, but limits is like the beginning of calculus. And so I want to make the connection between limits and calculus, and so you can actually see why are you learning limits, and like, how does this connect to when you take calculus? For those, some people don't have to take calculus, but I think about half of our class does. So I thought this would be good prep to get you ready for that class. So basically, the concept of what the derivative is something that you learn in calculus. It is a it's an equation, but it's also an action. You'll be told to take the derivative. So it's sort of a noun and a verb. And the concept is connected to things that we've already talked about before: slope of a line, and then average rate of change between 2 points. So those are like how where the concept of the derivative comes from. And the invention of the derivative was actually done by two people independently, Isaac Newton and Gottfried, or I think it's Gottfried Leibniz. I know for sure his last name is Leibniz. They both invented calculus at essentially the same time, and it's based off of this concept of finding average rate of change and slope. So we've got our slope formula, y2 minus y1 over x2 minus x1, and then we've got average rate of change, which is essentially the same formula, but it's not just for lines. You can use it for curves. So you have 2 points, and you're just estimating, finding the average that it changes by finding the slope of a line that would connect those 2 points. And so average rate of change is basically the slope of 2 points on something that's not a line. So if you were to connect it with a line. And the derivative is taking this same concept and going a step further. So I mentioned that it's basically an equation. What it does is it gives you the instantaneous rate of change at any point. So instead of taking 2 points and you're finding the slope between them to get an average rate of change, it's saying, well, what if you can find an estimate for how much is changing at that specific point in time? This is usually over time. So it's not like between like 1 second and 2 seconds, but at second 1, what is its current rate of changing? How much is it changing? This is why it's called instantaneous, because it's at the time that it's occurring. This is best represented by your speed. So we have our distance equals rate times time formula that you can use, and you can use that to find the average speed. If you know you drove 650 miles and you did it in like 10 hours or something, you can find your average speed along the trip, but you don't know the speed in any point in time during that trip. The derivative allows you to do that. It allows you to say, okay, I know this is the average speed over the whole length of the trip, but how much did it, was I going at any specific time? Maybe there were some times where you were driving like 25 miles per hour because you were in a slow town, and then sometimes you're going like 70 because you're on a good highway. It averages out to like 65 miles per hour, but you're not doing that the whole time. And so the derivative allows you to see, well, at this point I was going 25, at this point I was going 45, and here I was going 70. And that's what the concept of the derivative is it's allowing you to get more information at any specific point of time. So when you have a line, your derivative is the slope, because it's a constant slope. It's constant rate of change, and it's the same speed everywhere. But for other equations, you're actually looking at the average rate of change, and you're just basically looking at your intervals between your 2 points getting really, 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 really small, so you can estimate that time at that specific point. So I'm going to click on this link to pull up this Desmos graph. So this is the same basic picture from the average rate of change. And so you can ignore all this stuff on the left, but basically, you know, let's say we have these 2 points, so we're finding the average rate of change between them. But if you want to know, well, what is the actual amount of change, let's say at this point right here, this is not going to give you necessarily an accurate number because it looks like it's actually like decreasing, like slowing down maybe. You know, if you're thinking about this as like a speed over time, because it's going down versus, you know, if you connect these 2 points, it's actually looking like it's increasing. The idea of the derivative is that you take your average rate of change formula, but you keep getting closer and closer to the actual point you're interested in. And that gives you a more accurate estimate of the instantaneous rate of change, basically the speed or whatever it's going at that particular moment in time. So the closer you get, the closer it's going to be to indicate what is that actual speed, which is what we call it. I'm just using speed because it's something that you can understand with distance and everything, but the derivative could be anything. It doesn't always have to indicate speed. It's just easy to think of the derivative in terms of showing you the speed of something if you have a graph of distance over time or something like that. So the idea is to get really, really close, and we want to get as close as possible. So you're getting, and we say that it's infinitesimally small. Like if you can get as close as possible but not being equal, that's basically what the derivative is doing. So this gives us the definition of the derivative, and this is called the limit definition. So this formula is essentially the average rate of change formula. Let me get my pen here. Basically in that denominator, so let's say our average rate of change, oops, well, that is not the average rate of change. This is f of x2 minus f of x1 over x2 minus x1. And so let's say I've got this graph that I was looking at, and this is my point that I'm really interested in, x1, and then f of x1, just that function value at that point. And I'm going to use a second point that's really close to it. And the difference between those x values we're going to call h. And that's just a common, sometimes they use delta x because it's the change in x. Sometimes they use h. But that's basically, we're saying we're picking a close where we have h be really small because it's really close to my initial point. So x2 is going to be that x point plus h. So that's where we get x plus h. And then in the denominator, what happens is that you'd have like x1 plus h minus x1, and that's how it cancels out to give you h in the denominator. So this is literally the average rate of change formula written where instead of having a specific point, we're rewriting it in terms of a difference or a distance from this point we're interested in and a little bit further. And we take the limit of it because we want to get that distance, that difference, to be close to zero or non-existent, basically, like I was showing on that graph. You want to get it as close to zero as possible so that you can get the derivative or the speed at that instant in time. So you're basically just taking the limit of the average rate of change formula, and we write it in the specific form. So that's where this connects to limits and why you need to learn about limits. This notation here is specific notation for indicating the derivative of a function. So it's basically an apostrophe there, like on the keyboard, and that's read f prime of x. And so that's what we use to indicate derivatives. So you have your function f of x, and then f prime of x is the derivative of it. And the definition of this in terms of like if you were to look at it in a graph, it is the slope of the tangent line at a specific point. So I've got another graph here. And this is actually, again, I'm using the same equation, but you can plug in any equation you have. Don't worry about all the notation here. But this is actually, the tangent line is basically a line that mimics, that has the slope and goes through the specific point. And so the point that you're interested in you can see that it forms a perfect line when you zoom in for a little bit. And so it's basically the tangent line. What we're doing is we're just looking at the slope as if you took that part that's curved and zoom in enough that it's flat. What would be the slope of that line? So that's, the more you zoom in, the flatter it's going to look. And that's what the derivative is doing. It's basically saying, I've got this point that I want to find like the speed of at this graph or whatever. If I zoom in enough, it looks straight. So let's find the slope of that straight line. And then that is my speed. So that's what the limit definition of the derivative is doing, is it's just zooming in enough that you can approximate it with a line, and then you're finding the slope of the line. So that's what the concept of the derivative is, and it's used so much. Like a lot of physics formulas you can derive the formulas in physics from doing calculus. You can actually get the formula for circumference of a circle by taking the derivative of area. What derivatives do is they're basically removing a unit or dimension. So like area is 2 dimensions. You take the derivative, you're now in 1 dimension. And because it's got this this fraction, if you have like a distance and then you take the derivative of distance, you're now going to have distance per time, which gives you your speed. So the derivative of distance is speed. You take the derivative of speed, which is like, you have like miles per hour, that gives you miles per hour squared, or usually we use in physics meters per second squared. It gives you acceleration. So these relationships between speed, velocity, acceleration, distance, like even area and circumference, they all are derived from calculus and from the derivative. So it's actually a very useful concept that pops up all the time. And that's the invention of calculus, is how we were basically able to have all the technology that we have today, because without the invention of calculus, we could not have done what we are currently doing. It really revolutionized math and science and just was a complete game changer. So the next things that I have are just, we're going to use the limit definition of the derivative. So I'm going to show you how this formula is used to find the derivative. So we've got this function f of x equals 3 minus 5x, and then I've put the limit definition of the derivative on there. So you've got that in your notes, and that's the formula that we're basically going to be using. So our definition of the derivative requires finding f of x plus h. And so that's why we have to learn about function notation and how you replace x in your function with something else. And we're replacing it with x plus h. So I'm just going to simplify this. And that gives us 3 minus 5x minus 5h. And I like to do that separately, so that way when I go to my limit definition of the derivative, I can go immediately to plugging it into the definition and then going from there. So I've got f prime of x equals, and every time you do this, you have to make sure you are writing down limit as h goes to 0, because that notation, that doesn't go away until you've taken the limit and h is gone, essentially. So as long as you still have like an h in your formula, or you still have, you haven't actually done the limit, that stays there. So we have f of x plus h, so that's 3 minus 5x minus 5h minus f of x. And always put that in parentheses, because when you're subtracting the whole thing. So you need to actually distribute that negative. And then this is over h. So once you've plugged it in, now it's just a matter of doing algebra, because now you're just simplifying the top, canceling out what you can. So we have f prime of x equals the limit as h goes to 0 We have 3 minus 5x minus 5h minus 3 plus 5x over h. And things cancel. You'll find this with a limit definition that a lot of things will cancel out on the top of your fraction. And that makes it really nice to simplify. Is you have a lot of things that will, anything that basically doesn't have an x or doesn't have an h is going to cancel out for the most part. And you'll be left with only the things that have like h in them. So if things don't cancel out like that, then double check what your math looks like. Double check that you plugged in x plus h correctly. Double check your signs, because if things aren't canceling out like that, that means you made an error. So we have f prime of x equals the limit as h goes to 0 of negative 5h over h. And we can cancel out the h's because we have one on top and one on the bottom. And so f prime of x equals the limit as h goes to 0 of negative 5. And then it's at this point that you would be plugging in, essentially plugging in 0 for h. But h doesn't exist. We would just get negative 5. So our derivative is negative 5. And that is the slope of this line. So this definition of the derivative does give you the slope of a line. So it does what it's supposed to, because we know that the average rate of change on a line is constant. It's going to be that slope. And so when you find the derivative of a line, it is the slope. And so understanding that, anytime you're given a function that's a line, you know what the derivative is. It's going to be the slope, which is really, really nice, because then you don't have to go through this calculation every time. It is a little, it's not hard, but, it's like, why bother doing all the calculations if you know that it's going to be the slope? But now you know why. Now you can see that it matches. Are there any questions on this example? Okay. So this is an interesting one. And so this is f of x equals 7. So if we were to think about what this is representing, this is f of x is the same as y. So this is basically just a horizontal line going through 7. And slopes of horizontal lines are equal to 0. So because the derivative is the slope of a line, when we do the math here, we better end up with 0. If we don't, then we made a mistake. So you can think about it. You can look at what your function looks like and then think about, well, is the slope going to be positive? Is it going to be negative? Do I know what the slope is, to double check your math? So f of x plus h, well, because we don't actually have x, it's still going to be 7. So it's exactly the same. And this is like a trivial case of finding the derivative. So I have the limit as h goes to 0 of f of x plus h, which is 7, minus f of x, which is 7, over h. And so 7 minus 7 is 0. You have 0 over h. And 0 divided by anything is 0. And so the limit of 0, as h goes to 0, it doesn't matter what h is, we're going to get 0. And so that matches because the slope is 0. So what you learn from here is that the slope, or I shouldn't say slope because we're talking about derivatives now. The derivative of a constant is always 0. And so if you have a function and it's constant, the derivative, which is how much it's changing, is 0 because it's not changing at all. That's what this means, is how much is it changing? It's not changing. If I go back to my other one here, I could say the derivative of a line is the slope. So these are two shortcuts, basically. So if you're finding derivatives of a line or a constant, you don't have to go through this process because you can just figure it out based off of, is it a line? Okay, so slope. Is it constant? It's going to be 0. So let's look at something that's now not a line. Let's look at this equation of a parabola. So if I was to graph this, it's going to be looking like something like that. And so we don't have, like, if I was to kind of think about having like a slope, like over here, our derivative or slope would be negative. Over here, it's going to be positive. It's going to change. Like it's not constant all the way over. So when we find the derivative, we're not going to get a single number. We're going to get an equation. And that equation will allow us to plug in numbers, and then it will give us a number as whether, oh, you get a -5 out. Okay, so that's on the left side here. Or you get a +5. Okay, it's on the right side where it's got a positive slope. So when you find derivatives of things that are higher than a linear, you get an equation that allows you to model if the slope's going to be like what the actual slope is at each point. And you can see that the slope changes depending on where you are located on the parabola. So first step, and I might actually do this in a different color, is to find f of x plus h. So x plus h. You know what? I'm going to run out of room here. So let me just do this under here. So you have x plus h squared when you plug it into f of x, plus x plus h plus 3. So we need to square the x plus h. This is one of our shortcuts that you learn, and you get x squared plus 2xh plus h squared. So you would FOIL that out or use the formula when you have the square of a binomial. And that we square these things quite a lot, so you kind of memorize what it's going to be, because when you're finding derivatives of things squared, you do this a lot. Then I have my plus x plus h plus 3. And there are currently no like terms, so that is like the whole thing that we're going to be plugging into our definition of the derivative. So now we're going to find the derivative. So f prime of x equals limit as h goes to 0. I have x squared plus 2xh plus h squared plus x plus h plus 3 minus f of x, which is x squared plus x plus 3 all over h. So we've got a lot of algebra to do here, and this is why you have to learn algebra before you do calculus, because calculus is applied algebra, essentially. You're doing a lot of algebra in order to do your calculus. So we need to simplify the top here. I'm going to start by distributing my negative, but what some people do is they will just kind of write it above like that, so that they don't have to rewrite every step so much, you know. So you can say, okay, that's actually negative x squared minus x minus 3. And we have things that cancel out. We have this x squared, that will be minus x squared, those cancel. I have a plus x minus x, and then I have a plus 3 minus 3. And so everything I subtracted basically cancels out, and I'm left with things that only have h in them. So we have 2xh plus h squared plus h over h. So if you're doing this right, when you subtract f of x, that should allow you to cancel out. Everything in that part should cancel out with something else. And if it doesn't, again, then that means you have an error somewhere in your algebra. So we need to simplify this fraction that we have that we're taking the limit of. And we do that by factoring out an h on top. So we're going to factor out the greatest common factor. And this is where you start seeing all of that stuff that we learned in algebra is coming together. And you're like, oh, this is why I had to learn all of this, because it's used in calculus. So when I factor out the h on top, I'm left with 2x plus h plus 1. And then that allows me to cancel out an h on top and h on bottom. And this is really important because we can't take the limit while h is in the bottom because you'd be dividing by 0. So we have to somehow be able to cancel that h out so that we can actually take the limit. So we have f prime of x equals the limit as h goes to 0. And we have 2x plus h plus 1. Because the other stuff canceled. So now the limit as h goes to 0, well, this h will go to 0. So this is how we indicate, like, when you take the limit, that it will like be 0 or it'll go somewhere, you know, that you can cross it out with this arrow and then write 0, and that's indicating that this is becoming 0 when we take the limit. And so when we take the limit, now we took the limit, h is gone, and our answer is 2x plus 1. And that is the derivative. So that is an equation of a line that will allow us to find the derivative at any point on that parabola. So if I redraw a parabola, something like this. So if I plugged in a negative, like let's say, we're looking at that, I don't know if that point's on the, I shouldn't put a y value there, but let's say we're looking at an x value of -1. Our slope, estimating the average rate of change, should be negative. If you use this formula to find the derivative at that point, you're plugging in -1. For x, you get -2 plus 1, you get -1. The slope at that point is -1. And so that matches that if you're trying to approximate that with a line, you're going to have a negative slope. On the other hand, if we were to maybe see, well, what's the slope at a +1? If you're trying to approximate it, it's going to be positive. And your formula will allow you to do that. You just plug in 1 into your derivative formula. That's 2 plus 1. Your slope is 3 at that point. And it's positive. It's telling you have a positive slope. So this formula allows you to find the rate of change at any point on your graph without having to redo, find the equation of a line, doing all of that kind of stuff. You find the derivative first, and then you can just plug in numbers, and it will give you the slope at that point, essentially. Are there any questions? Okay, so the one thing that you can learn from this is that derivatives of quadratics are always linear. So anytime you have a quadratic equation and you take a derivative, it becomes linear. And that's because the derivative is removing a dimension. So instead of having x squared, you're now down to x. And so you have a linear equation. You can see that the process is kind of it's not really time consuming, it's just tedious. And once you get into calculus proper, there are shortcuts that you can learn so that you can find the derivative without going through this limit definition. Because if you do enough of these, you'll notice a pattern, and then you're like, oh, there's actually a formula that we can use to find the limit, or to find the derivative. But at the very beginning, you learn using the formula, the official definition, and then you can come to appreciation when you're like, oh, thank goodness there's shortcuts to this. We don't have to do this every time. Okay, so this one now we have a cubic, and if you're following your ideas here, the derivative should give us a quadratic because we're removing a dimension. So instead of going from x cubed, we're going to get an x squared in our derivative. I have the website for Wolfram Alpha here because you're going to want to have some help. You're not going to want to do all of this by yourself. So here's what I'm talking about. When I need to find f of x plus h, and I plug that into our cubic, we have x plus h cubed minus 12 times x plus h. Well, that's not easy to do by hand. If we were to try to do this by hand, you can do x plus h squared first and then multiply it by an x plus h. I can distribute that negative 12 through. We know x plus h squared. But you can see that if you go to multiply this, it's tedious. Because now you're going to have to multiply this x squared plus 2hx plus h squared times x plus h and simplify, and it's going to be multiple steps. So I recommend taking advantage of Wolfram Alpha, especially when you are, in calculus and you're doing this. So I don't think I made this one a clickable link. I think I forgot to make this one clickable. Yep. Okay, so let me pull up my Desmos and then we'll just type it in. It's all right. So Wolfram Alpha, there's lots of websites that you can do to do algebra, but I like Wolfram Alpha because it's not, they've got like examples of how to do this stuff, and it does calculus. It does a lot more than just algebra, and that's what I really like about it, is that it's useful for a lot more things. And it doesn't just show you, like, it won't actually show you the steps, which is great because you can't use it for cheating, but at least you can use it to do like the basic algebra. So we want to basically, I want to show you how to find this cubic thing that I have here, the x plus h cube, so that way you can not have to go through all these steps because it's going to take a long time. So what you do is, this is called expanding. So you can just type in the word expand, and then you type in what you want to expand, x plus h cubed. And there you can use a keyboard here. They have a phone app as well, but that's what we want to do here because we want to have it all multiplied out and we don't want to have to do it by hand. And so you can get step-by-step solutions. You have to pay for it. I think they might give you some free. Yeah, so, and the way it shows it to you is not helpful. You're probably like, what the heck is this? So I wouldn't rely on that. But all we care about is, okay, what does this actually multiply out to? Oops. And then you can click on it and it will give you some other information and stuff. And it gives you way more information that you need. But this is what we care about right here, is the result. That's what we are looking for. So this whole cubic thing comes out to, and h cubed plus 3h squared x plus 3x squared h plus x cubed. And then I have my minus 12x minus 12h. And none of this is like terms, so we can't combine anything at any point. So this is why I recommend maybe bookmarking Wolfram Alpha, because it will it skips these two steps and you save the time of having to multiply out the x squared plus 2xh plus h squared by x plus h. You can just do it in one step, and that will just make your life a whole lot easier. So we now have our f of x plus h. Now we need to actually take the limit. We haven't even done the limit yet. So we've got f prime of x equals the limit as h goes to 0. And I gotta write down my big giant thing here, which I have it on a sheet of paper. Let me get that out so I don't have to keep going back each screen. That will be a lot easier. Okay. H cubed plus 3h squared x plus 3x squared h plus x cubed. And then we're subtracting our original function, f of x, which is x cubed. Oops, I'm missing some stuff here. I'm missing the minus 12x minus 12h, and I'm running out of room, minus our x cubed minus 12x all over h. So I'm kind of making this work because I'm running out of room here. You can see where you are going to take like a whole line on a sheet of paper to do this stuff by hand. But we can cancel things out here. So I have the limit as h goes to 0. And when you cancel stuff out, you're going to end up with h cubed plus 3h squared x plus 3x squared h minus 12, h all over h. So everything that doesn't have an h basically gets canceled out, and you're left with only the things that have h in them. So just like the quadratic example, we need to factor out an h. So I'm going to factor that out on top. So I limit as h goes to 0 of h times h cubed, I'm removing an h squared plus 3hx plus 3x squared minus 12. You can see where it'd be really easy to make a mistake. So you have to be very careful, make sure you're writing down stuff correctly. So the h's cancel. So this gives us the limit as h goes to 0 of h squared plus 3hx plus 3x squared minus 12. And then you take the limit, and anything with h basically goes to 0. Because when you take the limit and you're thinking as you get close to 0, you can plug 0 in here, it's just going to be 0. So we get as our answer, our derivative is 3x squared minus 12. So you can see that this process gets very, very lengthy. And luckily, we have formulas so that you don't have to go through this limit process each time, because it's very, very time consuming. But if you do, you want to be able to use technology as best you can to simplify and help you with some of the algebra steps so that you can focus on the actual calculus of it and not waste your time on all of the algebra. So here's another example, and we're going to use Wolfram Alpha to help us out here because we are going to have fractions upon fractions. So we've got f of x, and then f of x plus h is 1 over x plus h minus 1. So that part's not so bad, not like the cubic. So now I'm going to plug it into my limit definition. We have 1 over x plus h minus 1 minus f of x, which is 1 over x minus 1 over h. So this is why we had to learn how to subtract fractions and do rational expressions, because now you have to combine and do that subtraction on top in order to simplify this. But I would just go to Wolfram Alpha and let it do it for you so that you don't have to mess up on that algebra. So in order to do that, instead of using the word expand, you use what is called together, because you basically want to take those two fractions and combine them. So we are doing together of 1 over x plus h minus 1 minus 1 over x plus h. And it's really important to make sure that you have parentheses, or not x plus h, it should be x minus 1. Really important to have the parentheses in the right place so it does what you want it to do. So I hit enter. And so you can verify, that it interpreted what you were doing correctly, that this is, yes, this is what we want. This is what we're looking at. We want to combine and do that subtraction. This is your answer here. Negative h over x minus 1 times x plus h minus 1. So we don't have to go through all the rational expression math. We can use this tool so that we can save us some time and some algebra. We got negative h over x minus 1 times x plus h minus 1 over h. So we basically have a complex fraction here where you're dividing a fraction by a fraction. And when you do that, essentially, if you're just dividing by h, that can just go on here. Because if you're dividing and then you're dividing again, they're just all in the denominator. And so you can see that then your h's cancel out. And so we have the limit as h goes to 0 of negative 1 over x minus 1 times x plus h minus 1. And so now when you take the limit, this h goes to 0, so that basically disappears. So we have an x minus 1 times x minus 1 in the denominator. So we get negative 1 over x minus 1 squared. And then that is your derivative. And you can see what I was talking about when I said that if you have distance, you take the derivative, you get speed because you went from meters to meters per second, and then you go from meters per second to meters per second squared. You can think of this function as meters per second, and we're resulting in meters per second squared because now we have a square in that denominator. So it matches with our concept of a derivative, and what the derivative does is it just keeps adding things to the denominator basically and then cancels things out as necessary. Are there any questions on this one? So this one is another one where you'll learn a shortcut on how to do this derivative. This one's not as bad as long as you have some tools. This one, so we've got f of s. So it doesn't have to be x. It could be any variable, any input. So we have f of s equals -2 times the square root of s. And so now we've got something going on with our square roots, and this one actually has a little trick to it that I want to show you. So first, f of, instead of x plus h, it's going to be s plus h because that's our variable here. So we have -2 times the square root of s plus h. So instead of f prime of x, it's f prime of s. You're still taking the limit as h goes to 0. And we have -2 times the square root of s plus h minus -2 square root of s all over h. So if we're subtracting a negative, that will actually give us adding. So we have the limit as h goes to 0 of -2 times the square root of s plus h plus 2 square root of s all over h. And then it's like, okay, well, what do we do here? Because we can't combine those square roots on the top because they're not alike. One is s plus h, one is s. So we learned in algebra how to rationalize the denominator. You can do the same thing with the numerator. So what you do is you multiply the top and the bottom by the same thing but with an opposite sign for one of the square roots here. And then we have to also multiply that on the bottom. And so this is where we want to go to Wolfram Alpha, because multiplying that top, where you're multiplying things with square roots, it's going to get gross. You're not going to want to try to do that by hand. So we're going to use Wolfram Alpha to do this for us to make it simpler. And so I'm going to go here. Now it's going to be kind of annoying to type this in here. So the extended keyboard allows you to do like square roots and stuff. So that is going to be very helpful. We're still going to use together. And now I'm going to do my best to try to type this in. So I have two fractions. So I'm just putting the two fractions in immediately. And so I have on my top, and again, I'm going to put parentheses because of the two fractions. I just want to make sure that I'm setting up everything correctly. And I wish that this was a little bit easier to use in this case, but I'm just like putting in enough parentheses so that I have a parenthesis for each fraction, and then within the fraction I have parentheses for the numerator and the denominator. So the numerator, my first fraction, I have square root of x plus, not x, oops, it's -2 square root of s plus h. And then it's plus 2 square root of s. And then that first fraction is over h. Now I'm going to type in the other one. Now, if you don't want to use this little keyboard here with the square root button, you can also type in SQRT to represent the square root. And so we're multiplying this by, and actually it's probably easier to just copy what I have here. Make sure I'm copying everything I want and just paste it in, but change it to a minus. And then let's paste it in, change it to a minus, and then I've got an extra, I think I have too many, let's see. And make sure I have enough parentheses here. There's one extra there. Okay. So I'm going to hit enter, and we want to double check that I entered in exactly what I wanted to enter in here. So we've got -2 s plus h plus 2s over h times -2 s plus h minus 2s, -2 times s plus h minus 2s. So this is basically what I wrote here. It is a little annoying to type it in, but it's better than trying to multiply this out by yourself. So your answer is this thing right here. So, move this over so I can copy this. So we simplified this thing, just making sure that I plugged everything in correctly. Minus, minus. So we've got, oops, equals the limit as h goes to 0. And I think I'm looking at this. I think they gave it to us upside down. So I know what this should come out to be, and it is not coming out to what it should be coming out to. So, okay. I also did this one by hand. We're gonna try a different website to do this just to verify. So Symbolab, this is another good website. This one is a little nicer to put things in for the square root, so this might work out better for us. So I'm going to put in parentheses, and then if I want to put in a fraction, you can hit your fraction button. And so we have -2 square root of s plus h. I have to hit my arrow, plus 2 square root of s all over h. And then I can put in my next fraction. And then I'm going to just again do, if I can, do copy and paste the top to kind of save myself some work. And change that to a minus and a minus. And then we'll hit go. Okay, so this confirms that this does simplify to the same thing we got from Wolfram Alpha. I don't know why I was thinking that it should be reversed. Well, this can't be right because we shouldn't. We've still got a numerator on the top. We should end up something on the bottom. Oh, that's okay. I see what it's doing. This is weird because when I did this before, it didn't do it this way. Okay, so Symbolab, it multiplied stuff out here, and then it just canceled out what we multiplied by. That's why it's giving us back the same thing we started with on the left. I'm like, that is not right. I know that's not right. I don't know why it is doing that. It shouldn't be trying to cancel that. It should be rationalizing the numerator. This is weird because I did this before and it didn't. Here, let's just take our initial thing before we were trying to rationalize. It's just splitting it up. Let's see. I can give it directions. There we go. Okay, this is what we're supposed to have it look like. Strange, because I did this before and I even wrote down that you use the together and it worked. So I don't know why it's not working today. So for your notes, Wolfram Alpha, just type in rationalize the numerator and it will do that for us. And then this is what it should be simplifying to. 2 square root of s minus 2 times the square root of h plus s. Okay, that is much better. I couldn't figure out why it wasn't. This is the downside of technology and these websites, is that sometimes they don't do what you want them to do. So you have to still understand what's going on. So luckily I knew that that couldn't be right. So I'm like, no, I've done this. Okay. So now that you've simplified everything, this is how it all simplifies to. And we're going to then take the limit as h goes to 0. So no, now we're just going to get 0. That's not right either. Why is this not working out? Because we're going to get 2 square root of s minus 2 square root of s, which gives us 0, which is not correct. So it is not even rationalizing the numerator correctly here for us. Which is interesting. Okay. Well, I think I'm going to have to do this one by hand. This is not what I planned. The technology is not playing with us today. We're going to have to do this one by hand. Okay, so I'm rationalizing the numerator. I have to FOIL out this nasty thing on the top. So I have to multiply my -2 square root of s plus h times -2 square root s plus h. That's going to give me 4. And then the square roots cancel and you're just left with s plus h. Inside, 2 square root of s times -2 square root of s plus h. That gives you -4 square root of s times s plus h. Those square roots can combine. Then outsides, -2 square root of s plus h times -2 square root of s. That gives you a +4 s times s plus h. And then 2 square root of s times -2 square root of s is -4. And then the square roots cancel and you're left with just s. Denominator, I'm going to just leave the h and then not multiply anything because we're going to end up wanting to factor out an h as possible as it is. Okay, so these cancel out. And the whole point of rationalizing the numerator was to get rid of the square roots on the top. So this gives me limit as h goes to 0. We get 4s plus 4h minus 4s all over this h times -2s plus h minus 2 square root of s. So notice the 4 s's cancel there. And then I can actually cancel this h out with that h. So what do we have? F prime of s equals the limit as h goes to 0. So everything on top canceled except we're left with a 4. And then we have this -2 times the square root of s plus h minus 2 square root of s. So now we're going to take the limit. So h here goes to 0. And we end up with 4 over negative 2 square root of s minus 2 square root of s, which is 4 over negative 4 square root of s. And then that simplifies to negative 1 over the square root of s, not 5s. And that's what we're supposed to be getting. I do not know why Wolfram Alpha was not behaving today for us, but we had to do it by hand. This is so weird because I did it on Friday and it worked just fine. But this is the trick that I wanted to show you here, is when you're dealing with things with square roots, your trick is to rationalize the numerator, and then you have to do all this math to simplify, but that allowed us to get our derivative here, which is negative 1 over the square root of s. And again, there is a shortcut rule for whenever you deal with taking derivatives of square roots, which would make this a lot easier problem to deal with. But you can do it. You know, it's just some algebra, and then make sure that you actually have to understand the algebra so that you know when the computer is not doing what you're telling it to do. Like when these fancy algebra solvers do not do what you want them to do. So that is basically all I had. I know this is probably, looks like, there's good, my screen's still working. Yeah, so that's basically what the derivative is. You're using the concept of a limit to find the derivative, to find the slope for all these different equations that could reference things, and they basically are allowing you to find how things change. And so once you get to calculus, you're going to learn shortcuts for doing all these things, so you don't have to take the limit every time. But it's super useful in anything engineering, or if you're coding anything where you're going to have to like solve equations, sometimes you end up having to code calculus, and so you have to kind of understand how all this stuff works. But now you've got a taste of what you're getting into if you're going into calculus, and it really is enjoyable. I love calculus because it's actually useful. That's where we take all this algebra we've learned, and now we can actually apply it to the real life, because most of real life is not constant, involves things that are changing. So I think calculus is really fun. So